we address the challenge of reconstructing long volumetric videos from multi-view RGB inputs using a novel 4D representation called temporal Gaussian hierarchy. The objective of dynamic view synthesis on volumetric videos is to present new perspectives of real-world dynamic scenes given input videos. This technology has widespread applications in fields such as film and game production, immersive remote communication, among others. The goal of our method is to efficiently perform real-time dynamic video synthesis on long volumetric videos up to 10 minutes. Previous method for dynamic video synthesis either suffer from poor rendering quality and rendering speed, or could only handle a few seconds of content due to excessive VRAM, training time, and storage overhead. Specifically, recent implicit scene representations like DynaRF and K-planes have achieved great success in synthesizing new viewpoints for dynamic scenes. However, as the scene complexity surges, for instance, in some cases with larger and more complex movements, they struggle to capture the intricate appearance details of these dynamic scenes, as illustrated in the videos. There's another line of work that employs a more powerful explicit scene representation such like point clouds or 4D Gaussians. However, these methods generally only operate on short volumetric video sequences, 1 tilde operator 2s. When applied to longer videos, these approaches require very large models that could not fit in memory. For example, for a typical 24 GB high-end consumer-grade graphics card, one could only fit a 300-frame sequence for 4 DGS before the model runs out of memory. To overcome these problems, we start from the basic 4D Gaussian splatting representation and identify its key limitations. Specifically, we need to address the training VRAM usage and storage overhead. For reducing the training cost, we propose a new 4D representation called temporal Gaussian hierarchy, which achieves a near-constant VRAM and iteration speed as the video length increases. To further bring down the storage overhead, we define a new compact appearance model that only enables high-degree spherical harmonics on demand. Gaussian splats in 4DGS are not organized and can lead to large training overheads for long sequences. However, we notice that the number of Gaussian primitives required for a particular frame should be a constant. Moreover, a typical dynamic scene will contain a large amount of temporal redundancy. Per these observations, we propose a hierarchical structure where each level consists of multiple temporal segments. Following 4DGS, we first define 4D Gaussian primitives using their 4D covariances, which can lead to a set of temporal influence ranges that denote the lifespan of the Gaussians. Then, a multi-level, multi-segment hierarchy is defined on top of the Gaussians, where the Gaussians are assigned to their respective segment using the equation on the lower right corner. This makes the temporal Gaussian hierarchy structure unique and makes sure that each 4D Gaussian is placed in the shortest possible segment. With the temporal hierarchy, we can efficiently sample the 4D Gaussians that influence this timestamp for rendering. Since the segments at each level don't overlap, the timestamp is influenced by only one segment at each level, which is identified using this equation. The computational complexity of this identification process is O log n, where is the total number of segments in the hierarchy. In practice, we place the temporal Gaussian hierarchy structure inside RAM and only copy the influence segments to the GPU memory. After each training step, the properties of the selected Gaussians are optimized with the reconstruction loss. So it is necessary to reassign the optimized 4D Gaussians back into their respective levels and nodes in the hierarchical structure. Notice that the optimization step is typically very small. Thus, the segments required for this update would roughly be the same as the ones used for sampling and rendering, ensuring its efficiency. Original 3DGS utilizes standard spherical harmonics evaluation to obtain the view-dependent color. However, the large number of bases in standard SH representation results in significant storage overhead, particularly when scaling to long videos. We observe that the diffuse part of the volumetric video does not necessarily require high-degree SH for accurate modeling, inspiring us to exclude this type of Gaussians to reduce the storage. Intuitively, diffuse Gaussians should receive a low-magnitude gradient on its residual SH coefficients H even when they are rendered and optimized as view-dependent ones. Thus, we can use a zero initialization and gradient thresholding strategy to successfully identify these Gaussians and retain their diffuse properties. Combined, Our proposed pipeline achieves the efficient representation of long volumetric videos. Not only can TGH utilize the temporal redundancy and varying view dependency for reducing storage overhead, but the efficient sampling process can also ensure a near-constant VRAM usage and iteration speed. Here we show the comparison of our method with 4DGS. As mentioned before, they run out of VRAM with longer sequences. Here's another comparison on an even longer sequence. Here's more comparison on the DynaRF dataset. Although the implicit method can also handle long videos, their rendering quality, 3D consistency, and rendering speed are significantly compromised. Here's another comparison on the ENI-RF outdoor dataset. Next, let's show some more real-time rendering demos of our method. Here's our method on the full length of some publicly available and newly captured datasets. Here are some more demos including viewing our method in VR using a headset. For more rendering demos, please scan the QR code for the project page or check out the video description. The code for the framework and rendering implementation of our method has been open sourced. Thanks for watching.